Hello guys, today I want to show you how to effectively deal with single factor ANOVA test. Now let's say the accompanying data resulted from an experiment comparing the degree of soiling from fabric washed with three different mixtures of methacrylic acid. Now assume that the measurements are normally distributed with equal variances. Now, first thing first, for us to be able to do the testing, we need to construct the ANOVA table, and then lastly, we then do the testing. So let's start with the first question. Now to do the first question, we need to add another column here on the table, a column for the raw sums. So we are going to calculate the sum of each row and get the total, which is called the grand total at the end here. So this is how we do it. So for the first row is 4.59. Then second row now it's 3.97. And the third row is 4.69. Now, the value that we are going to get here is what they call the grand total, which is like this. Its symbol for representing it is this one, x dot dot. So we're going to say 4.59 plus 3.97 plus 4.69, which is equals to 13.25. Okay, fine. Now the formulas that we are going to use are these ones that are familiar with our calculations. So basically we have this formula SST, which is the total sum of squares. So it is like this. J Xij, which is an observation, squared minus double squared divided by Ij. And then our sum of treatment sum of squares will be TR. This is another formula that we'll be familiar with. I divided by J O squared minus the same, squared divided by Ij. Note that we call this the correction factor. These are the formulas that we are going to use to calculate the treatment sum of squares and the total sum of squares. And the other one is the ANOVA identity. Sum of squares or the error will be equal to SST minus SSTR. So basically this is derived from the identity code, which is originally written as SST is equals to SSTR plus SSE. Now, therefore, we have this right now. Now, let's construct our ANOVA table. Now, this will be the column for the degrees freedom, column for the sum of squares, the mean squares, and the test statistic. This will be the treatment, and the error, and then the total row. So we'll have to find the degrees of freedom for treatment. Treatment is a sample. So we're going to find the degrees of freedom for the treatment. The number of samples that we have here is I. We have got a sample I with j columns. So I is 3 and columns is 4. So you come here and you count. You've got 1, 2, 3, 4, 5. Oh, sorry, it's 5 columns. 5 columns. And then we've got 3 rows. 1, 2, 3. 3 rows. These are your treatments. 1, 2, 3 are your treatments. And 1, 2, 3, 4, 5 are your columns. So your I is the number of columns and your J is the number of, your I is the number of treatments or samples, and your J is the number of columns. Now, let's get started. The formula for the degrees of freedom for the treatment is I minus 1. So which means in this case, it's going to be 3 minus 1, which is going to be 2. Therefore, write it here, 2. Now, the formula for the degrees of freedom for an error is I into j minus 1, which is equals to 3 into 5 minus 1, which is 12. 5 minus 1 is 4. And lastly, the degrees of freedom for the total is I multiplied by j minus 1, which is 3 times 5 minus 1, which is 15 minus 1, which is 14. So it's going to be 12 and 14. Now, how do you find the sum of squares? Now, we're going to start with the sum of squares of the treatment. So, note that we already have calculated the grand total. So what we read right now is this part of the formula. We already have the I and the J. So what we need right now is this part of the formula. Now how do we find this? All we do is to square each of the row sums here and sum them and divide by J, which is 5. So this will be, let's find this first. X bar squared divided by J will be 4.59 squared plus 0.97 squared plus lastly 4.69 squared, then divided by 5, which will be this will be 11.76502. Now what we do right now is to calculate the sum of squares of the treatment, which would be 11.76502. Note that we subtract this with the grand total squared divided by ij, right? So now grand total is given as 13.25 and our I is 3 and our j is 5. So all we need to do is to minus 13.25 squared divided by 4 times 5, which should be 0.06 0 0.85 rounded. Columns are smaller. Let me expand it a little bit. So it will be 0.06085, the first one. So the second one, note that we need to find the total one, the third one here. So to find the total one, we need to square each of the observations that we have in the data from 0.56 to 0.93, and then add all of it. Add all the squared observations, and then subtract them from the same correction factor which we used here. So now this is this. So to avoid tediness, I will not write it here. I will not write everything down. So I'll just write the final mark. So everything I'll do it in the calculator. .56 squared plus 1.12 squared plus 0.90 squared plus 1.07 squared plus 0.94 squared plus 0.72 squared plus 0.69 squared plus 0.87 squared plus 0.78 squared plus 0.91 squared plus 0.62 squared plus 1.08 squared plus I made a mistake here. It's actually 0.7. So it's 1.07 squared plus 0.99 squared plus 0.93 squared, which is 12.1351. Now let's calculate the total sum of squares, which will be 12.1351 minus the correction factor, which is 13.25 squared, divided by 4 times 5. And this will be sorry, I made a mistake here. It was 3, sorry. 3, even here is 3. Which is 0.4309. 0.93 rounded. So I can add it to the table. 0.43093. Now, what you can do to find the SST is to use the ANOVA identity. SST minus SSTR 0.43093 minus 0.06085. Let me verify that. Yes, it should be no 0.37008 rounded. can write it here now. Now we're about to finish. Now we need to calculate the mean squares. The mean square for treatment and the mean square for the error. Note that there is no mean square for the total. It's only the mean square for the treatment and the mean square for the error. So the formulas that you are familiar with, formulas that are used are these ones. For treatment will be, you divide the sum of squares for the treatment by its degrees of freedom. So it's going to be SSTR divided by I minus 1. So in this case, we have got 0.06089. Sorry, I wrote 9 here. It's 5. So divide by 2, which will be this is 0.0304 rounded. And now the other one, mean square error, will be sum of squares, the error, divided by its degrees of freedom, which will be 0.37008 divided by 12. Which will be 0.03084. Now, what you're left with right now is to calculate the test statistic. To find the test statistic, the formula that is used is this one. You divide the mean square, the treatment, by the mean square, the error. So in this case, we have got 0.0304 divided by 0.03084. The answer is 0.9857. Now we are done with constructing our ANOVA table. Now let's go to the second question. Test the hypothesis that the true average degree of the soiling is the same for all the three mixtures at 5%. At 5% level of significance. Now, firstly, we have to write down our null hypothesis and our alternative hypothesis. Our null hypothesis will be population mean of treatment number 1 is equals to that and that. And then the alternative hypothesis will be at least 2 of the population mean are unequal. Sorry. Note that there is no upper tail test, no lower tail test, or two-sided test here. Well, yes, we are dealing with one-sided test. Actually, we are dealing with upper tail test, sorry. Yes, we are dealing with an upper tail test, but there is no lower tailed or two-sided, right? Now that is our null hypothesis and our alternative hypothesis. Now, our test statistic, we found it from the table. It is 0.9857. Now, what we need to find right now is the critical value. Remember, we're testing at 5%, sorry, which is 0. Alpha is 0.05. Now, if you can use p-value approach, but right now I'm going to use the critical value approach only. Now what you need to find is the critical value, 0.05. Now remember, for the F distribution, we have got 2 degrees of freedom. The numerator degrees of freedom and the denominator degrees of freedom. So in this case, our treatment degrees of freedom is the numerator degrees of freedom, and our error degrees of freedom is our denominator degrees of freedom. So it's gonna be 212. To find this, you can use the tables. You can either use the tables or Excel, softwares like Excel. So let me try to find quickly. .05. By the way, right now I'm using Excel, but you can use tables to find this. Two and 12. So answer is 3.89. Now, we have to make a decision whether we reject the null hypothesis or not. So in this case, we will not reject the null hypothesis because the critical value, or let me say the test statistic, is less than the critical value. So our decision, will be that we do not reject the null hypothesis, since f is less than 3.89. We would reject it if our f was greater than 3.89. Now our conclusion will be that at 5% level of significance, there is enough evidence to support the claim that the true average degree of soiling is the same for all three mixtures. This is it.